Okay, moving on to video 412. Here we're going to define acids and bases in a couple of different ways. Note there are other types of definition, or there are other definitions of acids and bases, but for the purposes of the AP test, you only need to understand these two. Okay, so we're going to define first what an Arrhenius acid is. An Arrhenius acid defines acids and bases based on what is produced when the substance is dissolved in water. Neutralization takes place when an Arrhenius acid and an Arrhenius base are combined. So neutralization means you're going to produce a neutral substance. And when you combine an Arrhenius acid and an Arrhenius base, you do that to an extent. So the definition of an Arrhenius acid is something that increases the concentration of hydrogen ions when you dissolve it in solution. So it gives off hydrogen ions. So for example, HCl, hydrochloric acid, will dissociate into H plus and Cl minus, thus increasing the concentration of hydrogen ions. HNO3, nitric acid, strong acid, will do the same thing. And this one, HC2, H3O2. That is acetic acid. This is acetic acid, also known as vinegar. You will see this a lot. It is worth memorizing what acetic acid is. So, memorize acetic acid, aka vinegar. You'll just see it in so many reactions, and it's just going to be worth it for you to memorize. So in vinegar, acetic acid is not on that list of strong acids and bases, so that is a weak acid. Okay, an Arrhenius base then increases the concentration of hydroxide anions in solution. So for example, that should be an E, sorry. KOH, potassium hydroxide, will dissociate into K plus and OH minus, and then also calcium hydroxide is a good example of this. Both strong bases. Okay, so looking at an example that kind of talks about neutralization here. Write the equation for the neutralization process that produces the salt calcium phosphate. So we can choose any acid and any base that are going to neutralize each other and produce calcium phosphate. So first thing to know is that an acid plus a base will always produce some salt. And of course, the salt doesn't just refer to NaCl. A salt is any ionic compound plus water. So I'm going to abbreviate this. HA is going to be my generic acid equation. So H for hydrogen ion, A for acid. And A is going to be the anion. So HA plus BOH, so the base, the positive part of the base, of course the hydroxide anion, goes to BA. So this B is positively charged because that's negative. This A is negatively charged because that's positive. So the salt is going to be BA plus H2O. That's water. Okay, so for my reaction, I'm going to choose phosphoric acid and calcium hydroxide because I want my phosphate to come from my phosphoric acid and my calcium to come from my calcium hydroxide. Of course, you can choose any two that have calcium and phosphate. So here's my phosphoric acid is H3PO4 plus my calcium hydroxide. And that's going to yield, so positive calcium, negative phosphate. So my calcium is +2, my phosphate charge is -3. So balancing that out, I have Ca3, PO4, 2, so a total of -6, +6, plus H2O. Going through and balancing my reaction here, should have a 2, 3, and I believe 6 waters. So there's your balanced reaction. So here, this was my HA, so the PO4 minus was the A minus, the H of course here. The B was calcium, OH was OH, and that B was calcium, just like before. And A, right here, was phosphate, A is phosphate, plus water. And so those H pluses and all those OH minuses all combine to form water. So that's an example of a neutralization reaction. That's one way to define an acid and a base, the Arrhenius way. Now, the Bronsted-Lowry way is a little bit different. Not all bases, for example, like ammonia, NH3, are net ionic hydroxides. So they're not going to just give off hydroxide in solution always. So we need another way to define bases. So here we're going to use the Bronsted-Lowry definition. That defines acids and bases based on proton or H+ transfer. Proton transfer processes are generally in equilibrium. Okay, so proton transfer just means H+ transfer, because if you think about it, a hydrogen ion is just a proton and then an electron. If the electron's gone, well, then you just have a proton. So we just say a proton. So a Bronsted-Lowry acid is a hydrogen ion donor or a proton donor. Bronsted-Lowry base is a proton acceptor. So the acid gives up the proton, the base accepts it. Something that is amphoteric or amphiprotic means it can do both. So water is a good example of this. So water can either accept an H+, or it can give off an H+. So it can act as an acid or base. So can both donate and accept H+. Okay, so many bases here. Note, many bases are not ionic hydroxides. And that's just like what we said before. That means they don't dissociate into hydroxide. Okay, example 5. Let's take a look at the Bronsted-Lowry definition being used. Write the proton transfer equation, so just the donor-acceptor thing, for the process when solutions of acetic acid and ammonia are combined. Identify the acid-base, conjugate acid, and conjugate base in this process. Now, you should have learned what a conjugate acid and conjugate base were in your first-year chemistry class. If you didn't, we'll go over it briefly. So, remembering what acetic acid is, HC2, H3O2, plus ammonia is NH3. So this is a good base to memorize, a good weak base to memorize is NH3, that's ammonia. And acids here are going to donate their proton. So if this acid, and I'm going to label this acid, and this base, if this acid donates its proton, this H+, what's going to be left over is the rest with a minus sign. So you're going to have C2H3O2 minus. And that H+ got transferred to the NH3, to the base. Because remember, a base is a hydrogen ion acceptor. So the acid gave up its hydrogen ion, the base accepted it. So if the base accepted that H+, I want you to predict what is going to be formed from that. Okay, so if the ammonia, if the NH3 accepted the H+, it now becomes NH4+, has an extra hydrogen ion, an extra positive charge too. So this is going to be your conjugate acid, and this is going to be what we call your conjugate base. So let's label those, and we'll talk about what that means. Okay, so the conjugate base just acts like a base in the opposite direction. So let's look at this. This is negatively charged here. So if this is negatively charged here, it's going to be able to accept a proton from a conjugate acid. So the conjugate acid is going to want to donate, just like an acid would, its proton. The conjugate base is going to accept it, because remember H+ acceptor, in the opposite direction. So if we had this arrow switch directions here, as in equilibrium, this would be your new acid, this would be your new base. So this acid right here and this base, this is what we call a conjugate acid-base pair. So this acid, the acid becomes the conjugate base, and the base becomes the conjugate acid. And that is always true. And we call this a conjugate acid-base pair. So these are conjugate acid-base pair. And that's the same here, conjugate acid-base pair. I don't really have room to write it. Okay, example 6. Write the dissociation equations for A, acetic acid, and B, ammonia. All right, let's do acetic acid first. So acetic acid, H, C2, H3O2, plus H2O. We're going to add that to water. And this is going to be in equilibrium. Because we have a weak acid here, it only dissociates partially, so it's going to go back and forth in equilibrium. Since this is an acid, it donates a proton, so we're going to get rid of this H and a positive charge, and be left with C2H3O2 minus, plus that hydrogen ion got transferred to water. And so now we have H3O plus. Okay, now let's do the same thing for ammonia. So NH3, throw that in water. Now ammonia is a base. And ammonia, since it's a base, is going to accept a hydrogen. Now it's going to accept a hydrogen from water. So the water is going to lose a hydrogen and give it to ammonia. And so let's see what we get here. We should have NH4 plus, and then whatever was left over of water here is hydroxide. It's plus OH minus. So interestingly, in this first reaction, we had water acting as a base, and in the second reaction, we had water acting as an acid. So giving up its proton here, accepting its proton here. And that's what we mean by amphiprotic or amphoteric. So for example, H2O. H2O is a classic example of something that's amphiprotic or amphoteric. It means either it can either accept or donate a hydrogen ion. So let's go ahead and label these. I want you to please pause the video, and in both of these equations, I want you to please label the acid, the base, the conjugate base, and the conjugate acid. Go ahead. Okay, so this is going to be your acid. This is going to be your base, right? Because here you accepted a proton. The acid becomes the conjugate base, so CB, conjugate base. And over here, the base becomes the conjugate acid, So that means that if you were to go the other way, this H3O plus is going to be the acid, it's going to give up the H plus. Conjugate base is going to accept it, and you're going to move the other way. Okay, next one, your NH3 or ammonia. Again, it's worth memorizing the formula for ammonia is a base. Here your water was an acid. Now the base accepted a proton, so that makes it a base. The H2O donated that proton. The NH3, the base, becomes the conjugate acid. The acid becomes the conjugate base. Okay, that's the end of video 4.1.2.